This picture here was taken by a Blu-ray player. Want to know how? This video will reveal it. Every optical disc player already contains what you need. After all, it must be able to see the microscopic pits on the disc in order to play it back. This is done by the so-called optical pickup unit, or OPU for short. An OPU is made of two laser diodes, one for red and infrared light to read CDs and DVDs, and one for violet light to read Blu-rays. The laser gets directed and focused on the disc through lenses and mirrors. And there it gets reflected and led to a matrix of 4 photodiodes, the PDI-0 photodiode integrated circuit. Here I have one under a microscope. The field in the middle consists of 4 photodiodes numbered from A until D. Their outputs are used to calculate the focus error signal, or FES for short. This indicates how far away the laser spot is from the focus point. If before or behind, the spot becomes elliptic and the focus error signal deviates from 0. So the value of the FES represents the distance between OPU and its target. If we add the values of these fields together, we get the sum signal, which measures the total amount of the reflected light. We can use both the FES and the sum signal for our purpose. There are also 4 more sensitive fields which we can use. But more detail on this in part 1. There I also show how sensitive this setup is. The FES even reacts to the tapping of my fingers on the bench, so sensitive that it can even record my voice. Check it out. To get our microscope, we need a mechanism to move the OPU and the sample against each other line by line. So let's build the mechanics first. After designing the parts in FreeCAD, I registered on the JLC PCB website and uploaded my 3D files. After a quick online check on how the parts will turn out, I had the choice between a whole lot of different materials. Hovering the mouse over the names reveals short descriptions of the material, so you can compare and find what best fits your needs. I went for the Lido 6060 resin because it has a high stability and low tolerances, which is just right for my project. All that was left to do then was selecting a carrier and placing the order. Then JLC PCB performs another verification, and if everything is okay, production can begin. A few days later, a packet from JLC PCB arrived. Let's see what's inside. Tension is rising. And here are the 2 parts. Look and feel lightweighted but still stable. Okay, but now let's start tinkering. This is the OPU on its LED as I salvaged it from the Blu-ray player. I am going to replace it by one of the 3D printed parts now. This platform will hold the sample in place later. The stepper motor with the spindle will move it in Y direction. Now I'm going to mount the OPU to the top part between the 2 threaded rods. And keep it in place with spacers, bolts and nuts. Now let's assemble this above the bottom part like so. That's it, a simple and straightforward construction. With the 4 knurled nuts at each edge, I can adjust the distance between the OPU and the sample. Now I'm coming to the electronics and software that controls this device. Everything is built up on 3 breadboards. The core is an ESP32 development board. 2 of its digital outputs are connected to an L293 motor driver IC. This drives the electromagnet that's responsible for the scanning in X direction. 3 of the other outputs go to a 4988 stepper motor driver module and drives the stepper motor that pulls the sample in Y direction. Another output goes to the transistor that controls the current through the focus coil. Then there is an LM317 for limiting the current through the laser. This also allows me to adjust its power. Finally, an MCP4006 operational amplifier IC computes the FES and sum signal from the PDIC output and feeds them into 2 analog input channels of the ESP32. Here a short glance on the schematic. If you are interested in this, you can pause the video there. As I already mentioned, I used an ESP32 as a microcontroller. This SoC is ideally suited for making web-based applications. That's why I made a small website based on JavaScript through which I can control the whole thing over VLAN using a web browser. But now let's give it a try. I can open the website out of Microsoft Code's File Explorer. There it is. Unfortunately, it does not fit into the flash file system of the ESP. This is because it's built around the OpenCV computer vision library and this just needs too much disk space. I put a piece of fabric on, place a cover glass on top to flatten it, and flip the OPU overall. Now the shooting can begin. There are 2 input channels. One is for the summarized PDIC outputs. This represents the total amount of light reflected by the sample. The other is for the focus error signal which I mentioned earlier. On the breadboard I also connected 2 LEDs to these channels. Now I carefully turn the knurled knobs to adjust the distance between OPU and fabric. And at one point the LEDs begin to flicker. After that I fine-tune the focus here on the website until the indicators at the bottom are fully deflected. Finally I reduce the power of the laser a bit. Otherwise parts of the image would be overexposed. The last setting is the scan speed. I set this to maximum and start the scan. Line by line the picture builds up, so I can check the exposure and if I got the right area. What I'm getting here looks good so far, but the image still appears coarse and grainy. So I go ahead and take a second shot. This time, however, I reduce the scanning speed. This increases the number of samples the AD converter takes per pixel and thus averages out the noise. This makes it take longer though, however the picture looks much better now. Let's have a quick look at the picture drawn by the focus error signal. Looks similar, but not as nice as the picture we got from the sum signal. The original resolution is 127 by 127 and I scaled it up to 512 by 512. That's why it looks a bit blurry. But you can still make out some details, like the tiny fibers from which the threads are spun. The scanned area is less than 1 by 1 mm, 127 scan points per line and 127 lines. That's best resolution I can get from it for now. To get more, I need to replace that spindle by one with a finer pitch. Let's put something else underneath and take another shot. What could it be? Wait a second. Does it remind you of anything? You are right. It is a PDIC from another DVD player. Let's toggle to the focus error signal. This looks a bit more detailed than the sum signal. That's because the FES depends more on the distance than the sum signal does. Thus it can resolve fine embossed structures better. Back to the sum signal. Doesn't show that much details. Here come some more images. Can you guess what it is? Now it's up to you guys if I'm going to make another video on this. Once this video has received more than 500 thumbs up, I will shoot part 3. So hit that like button if you want me to. Also consider to sponsor these channels to help me make more videos. And you will get ad-free previews. Check it out. That's about it. See you next time.